Okay, hi everybody. We're going to start. Okay, so as you know, and Von Ahn likes to allude to when he teaches this class, it's a bit of a lie, the title. Some of the topics are more great theoretical ideas in math than in computer science. And today's lecture is admittedly going to be a bit like that. I'm going to give you some computer science applications at the end. But it's mostly going to be the mathematics of polynomials. Now, luckily, polynomials are like the one mathematical object that I think all computer scientists in every area agree are awesome and highly relevant to their work. So I think it'll be worthwhile for us to talk about them today. Okay, so the first thing I have to mention is I have to briefly talk about fields, because that's another topic, because polynomials like to live in fields. So you may ask yourself, what is a field? It's a mathematical number system. So this is a quote that some former lecturer for this class, Guruswamy, found about fields, which is quite amusing. We're going to find out about this special kind of field where 2 is 0 and plus is minus and squaring is a linear operation. So I borrowed this quote, but actually I looked up who this person is. He's an interesting character. He's actually a well-known computer scientist. He worked mainly in cryptography. He designed some candidate encryption schemes for like AES and SHA-3. And he's also the first person to observe that factoring numbers can be done in like less than brute force, like less than 2 to the number of digits time. So he's also a witty guy for making comments about fields as well. Okay, so what is a field? First, I'll give you the informal definition, which is easy, and it's actually enough for you to get along in life. Basically, it's a number system, a system of numbers where you can add, subtract, multiply, and divide by non-zeros. Okay, so I'll just give you some examples that I think you're all familiar with. The real numbers, the rational numbers, the complex numbers, and you're going to have to know about the complex numbers if you don't already, because we'll use them a lot when we talk about quantum computation in a few weeks. So don't be scared. And also the integers modulo a prime. This is something that we talked about 2 lectures ago. We observed that when you're looking at the integers mod a prime, in addition to adding and subtracting and multiplying, you can also divide. Let me give some examples of some well-known number systems which are not fields. I really don't know where the name field comes from, by the way. It's just the name. So the integers. So why are the integers not a field? Yeah, you cannot divide. I mean, you can divide, but then you go outside the integers into the rational numbers. Okay, so integers are not a field. There's no division. How about the positive real numbers? What? Yeah, you can't subtract. So addition is no problem, multiplication is no problem, division is no problem, but you cannot subtract. I mean, you would go outside the positive reals. Okay, that's basically the notions you need to know. Since we're here, though, let me give you a very formal definition. You would see in a math textbook, and it interacts with what we saw last time about group theory. So a field, formally, is a set F, that's your set of numbers, and it has 2 binary operations called plus and times. Okay? So here's an example, the integers mod 3. We used to call that Z3. When you're thinking of it as a field, it's traditional to call it F3. So sorry about that, but F3 and Z3 are the same thing. The integers mod 3. So this is a table of addition mod 3, and this is the table of the binary operation for multiplication mod 3. So you can check that I did it right as I continue to talk. So what properties should a field have? If you just look at the numbers in F with addition, that should be a group. And furthermore, it should be an abelian group. And its identity element is called 0. So this basically says that you can add and you could subtract, and there's a number called 0, which is the additive identity. Okay, and that addition is associative and commutative like you expect it to be. Similarly, there's a similar rule for the multiplication. It says that if you take F and delete 0, you don't want to have 0 because 0 does not have a multiplicative inverse. Then F without 0 together with the multiplication operation also forms an abelian group. So you can multiply and divide, and multiplication is associative and commutative like you expect. And you call its identity element 1. So every field has at least 2 numbers in it, 0 and 1, probably more. And there's one more rule for being a field. So the 3 rules of a field are this one, and this also simple looking one, that the distributive law holds that multiplication and addition interact in a gentlemanly fashion that you expect. Multiplication distributes over addition. Okay, so if you have a set of objects F that satisfy all these laws, then it's called a field. Mostly we'll just see some familiar examples of fields. Any questions? Okay, so let's look at some examples again. So fields, as we've already seen, they can be infinite or finite. We saw an example of a finite field and some examples of infinite fields. Let me talk a little bit about finite fields because these are mostly important for computer science because, computers are finite objects, so they like to work with finite things like finite fields. So as I said, there's some infinite ones, so like rationals and reals and complexes. And some finite fields we already know. The integers mod p, where p is a prime, is a field, and it's finite. Okay, so I'll ask you some questions. Is there a field that has exactly 2 elements? You can shout it out if you like. Wait, I was expecting yes or no. Yes, there is. The integers mod 2 is a prime, form a field. Okay, so yes. Is there a field with 3 elements? Yes, I showed it to you before. It's the integers mod 3. Maybe there are some other ones, but we at least know there's one. Is there a field with 4 elements? Shout it out. Don't know. Some sophisticated people are saying yes, and they are correct. There is a field with 4 elements. I will not tell you what it is, but for now I will tell you this interesting fact that it exists. In fact, you can go home and verify that if you call your 4 elements 0, 1, a, and b, and this is your law for addition and this is your law for multiplication, you can verify, and it's quite laborious, that all of the laws of fields from the previous slides hold. So you can entertain yourself later by checking that. But this is a fact I'll tell you. Okay, is there a field with 5 elements? Yes, the integers mod 5. Is there a field with 6 elements? Take a shot at it. Take another shot at it. No. Yes. This is actually harder to prove because, you have to somehow prove that you cannot have a field with exactly 6 elements. It's not obvious how you would do that at all. In fact, it's not so easy, but somebody did it. This is not a math class, so I'll just assure you that the answer is no. Is there a field with 7 elements? Yes. Is there a field with 8 elements? You want to guess? Half of you are right. The answer is yes. Is there a field with 9 elements? I'll stop making you guess. The answer is yes. 10 elements? No. Okay, now I'll make you guess. What numbers are such that there's a field with that many elements? Yes, you guys are very good at this. Primes and prime powers. Anything that's a power of a prime. This is a theorem. This theorem is very hard. I mean, you would prove this in like a senior level algebra class. For a finite number q, there's a field with q elements if and only if q is a power of a prime. Okay, so if q is a prime, we know it. I mean, there's the integers mod q. Otherwise, it's hard. Furthermore, it's unique. For each q that's a power of a prime, there's essentially only one field with q things. What do I mean by that? Any 2 fields that both have q elements are basically the same thing up to isomorphism. So if you just rename the elements of this one to that one, the laws of addition and multiplication are the same. Any questions? So actually, I'm kind of just telling you this somewhat for fun. This is called the field FQ. It's kind of unique because there's exactly one of them really for each q. But it's sort of just for fun. For the purposes of 251, essentially you should only remember that there's the integers mod a prime are a field. There are also some other fields. And I'll even tell you what they are later. It's hard to just say in a table what the addition and multiplication are. But that's the facts about finite fields. Any questions? Okay. I think that's all I have to say about fields. So now we can talk about the main topic, which is polynomials, which you've probably encountered before in your life, but we'll warm up to them again. Okay, so again, I'll start with an informal definition. A polynomial is basically an expression. Think of it like a syntactic object, an expression that looks like this. Okay? So the x here is a symbol called the variable. And these numbers, which stand next to the powers of x's, are called coefficients. Okay? So the x is raised to various powers, and then next to it are some numbers that are coefficients. Okay? What kind of numbers? Well, that's why I told you about fields. So Coefficients, a polynomial lives in a field. So there's you fix a field, and then the coefficients can come from that field. Okay? You can also allow polynomials with multiple variables. I won't talk about that in this lecture, but maybe it'll come up on the homework, for example. We'll see. Keep it simple. So if you have a variable symbol x and you have a field f, then sorry for the notation overload, but f square brackets x means the set of all polynomials with variable x and coefficients from the field f. So this fellow up here is in the real numbers with x. It's a polynomial with real coefficients. Actually, it's also in the complex numbers with variable x. And I guess it's actually even in the rational numbers. I mean, these happen to be rational numbers. But anyway, you fix a field, and that's where your coefficients come from, and then you have a variable. OK. So again, let me give you a formal definition. This actually will mainly serve to tell you the definition of what. Oh, yeah, question? The question is a good question. If you fix a field, does f have to come from that field too? The answer for now is x is not a number. X is only a symbol so far. So x is just like a letter for now. Later, we're going to talk about evaluating polynomials at field elements, in which case the answer will be yes. But for now, just think of this as like kind of like a formal string. X is just a symbol so far. OK, excellent question. OK, formal definition of polynomials. So fix a field f and a variable symbol x. So f of x is the set of polynomials over f, and it's defined to be all expressions that look like this. OK, so you have a coefficient c sub d times x to the d plus another coefficient times x to the d minus 1, all the way down to x to the 1, and a coefficient just by itself, c0. And each of the coefficients should be in the field. And I'm going to insist that the top coefficient, the one standing next to the highest power of x, is non-zero. Because if it's 0, you should just imagine deleting that one. OK, so it's like a formal expression. Yeah?
To be clear, are the powers always going to be integers?
Oh, yeah. I didn't actually say that. But the powers are always x to the 0, which you don't write, x to the 1, x to the 2, up and so forth. So x to a natural number. Yes, I should have written that, actually. OK, so this is an extra definition. We call d the degree of the polynomial. So it's the highest power of x that has a non-zero coefficient on it. OK? Good. Now, actually, there's a very slight screw-up with this definition. Can somebody see it? Strictly speaking, there's one polynomial that exists but does not fall into this category. Yes? Yes? Yes. Yes. I did it this way so that I could define degree, but now if you stare at it carefully, you see the polynomial where everything is 0 is not allowed, but it is allowed. Okay, so I'll just say also the expression 0. Remember, 0 is in every field. 0 is also a polynomial. Now you have to decide what the degree of the 0 polynomial is, and it's like one of those like very annoying questions, like, oh, what is 0 to the 0? It's up to you. People take different definitions. It's not really important. It's most convenient to define its degree to be negative infinity, but we're not going to stress about that. Just the 0 polynomial is always a special case that you have to annoyingly talk about. But every other polynomial has a nice degree that's a natural number. Okay. Any questions about degree? Okay. Okay. Adding and multiplying polynomials. This slide is simple. You can add and multiply polynomials. And it works just as though you might imagine and have already seen before. So here are two polynomials, and just sort of to get used to the notation. They're living in f11 sub x, which means you think of their coefficients as the integers mod 11. That's p of x, that's q of x. So p of x plus q of x is, you just add them. Now, while I'm here, I can also say that here we have a coefficient that's 15, but we're thinking of the coefficients mod 11. So you could also call it 4. All right, and these polynomials are the same thing in this field, okay? Because like 15 equals 4 mod 11. You could also, if you want, call negative 1 plus 10. And maybe if you're like, I don't know, writing a quiz or something, you should bring all your coefficients to numbers between 0 and 10 in this case. But that's for the convenience of the TA. These things are all equal mathematically. Okay, that's adding two polynomials. It works exactly like you expect. You can also multiply two polynomials. It works exactly like you expect. It's like FOIL or whatever. You do it in high school. So here you multiply it all out, and you get some expression like this. And then, it's probably good form to further reduce the coefficients, in this case, mod 11. So maybe the 15 becomes a 4, and the 50 becomes a 6, what have you. Okay, questions? Now, this is kind of fun. And we have this set of all polynomials over a field. And we have a way to add them, and we have to multiply them. Maybe we can, take it to the next inception level by observing the following facts. The addition of polynomials is associative and commutative. You can check that. You can subtract. There's a zero polynomial which serves as an inverse. So the set of all polynomials with addition as the operation is an abelian group. Yeah? Oh, yeah, sorry. F11, for some reason, when you're talking about fields, this means the integer is mod 11, which we used to denote by Z11. But somehow, if you think of it as a field, you call it F11. No, so this is the field, F11. That means the set of integers mod 11. It's a field. And then this bracket X means, when you put it together with the field, this object denotes all polynomials over the variable X with coefficients from the field of integers mod 11. So they can have any degree. Good? Okay, so, so the set of all polynomials over the field with addition is also an abelian group. So a little callback to the group theory lectures. Also, multiplication is associative and commutative, and there's an identity element, 1, the 1 polynomial. And also, multiplication distributes over addition like you'd expect. So this is actually kind of awesome. It sort of almost looks like f of x, the set of all polynomials, is itself a field. But that's wrong. There's one thing that's missing. Can somebody say what it is? Say it louder. Yeah, multiplicative inverses. You cannot divide, in other words. So if it were true that p of x divided by q of x was always a polynomial, then that would be cool, and f of x would itself be a field. But it's not true. It's like the integers. That's the one thing you're lacking. Now, actually, you might say, well, in integers, it's true. If you divide two integers, you don't get another integer. But there is some notion of division in integers, right? Like integer division with remainder. And this occurs also for polynomials over a field. And in fact, there are many analogies between the integers and between the set of polynomials over a field. And I'm going to tell you a little bit about these analogies, and maybe it'll help you warm up to the class of all polynomials over a field. So as I said, Z has the concept of division with remainder, and that's what it means. If you have A and B, and you try to divide A by B, B should be non-zero. You can sort of do it by saying A can be written as Q times B plus some remainder R, where R is smaller than B. Right? That's integer division. And f of x has exactly the same concept. So if you have two polynomials, a of x and b of x, this is a typical notation for a polynomial, and b is non-zero, you can also sort of divide a by b, and you get some quotient polynomial q, and you get some remainder polynomial r. And what's this notion of smaller than? It's in terms of degree. So this division has the property that the degree of the remainder is smaller than the degree of the thing you're dividing by. So it's a nice analogy with Z. Let me give you an example. Polynomial division. It's like division with remainder. So suppose I say, here are two polynomials, 6x to the fourth plus 8x plus 1, and this one, where the symbol is x and the coefficients are mod 11. So divide. So you do it just like in elementary school. Maybe you've done this before at some point in your career. You draw this little table, like 2x squared plus 4 into this thing. And you first try to make, you look at the largest part and try to multiply it by something to get that to match up. So you should choose 3x squared. I'll do this example. Hopefully you'll get the gist of it. So you multiply this thing by 3x squared. You get 6x to the fourth plus x squared. Then you subtract. And you get minus x squared plus 8x plus 1. And then you say, I should multiply this divisor again by something to match up with the highest degree here. So I guess I'll multiply it by 6. No, 5. Darn it, 5. If I multiply it by 5, I get 10x squared plus 20. But we're doing mod 11. So 10x squared plus 20 is the same as minus x squared plus 9. So these match up, and you could subtract. And you get 8x plus 3. And now you're done, because this is like the remainder, and it has degree strictly less than this divisor's degree. The divisor has degree 2, and this remainder has degree 1. Okay, and so you've solved the problem. I hope you got the gist of it, because it's very much like long division. And you can check that indeed the 6x to the 4th plus whatever is the quotient, 3x squared plus 5, times the divisor plus this remainder, polynomial mod 11. Any question about that computation? I'm not sure we're going to make you do stuff like this, but it's good for something I'll say later. Okay, so let me complete this one slide of analogies between the integers and polynomials. So in the integers, we have a notion of size, which is like the absolute value of an integer. And in polynomials, there's also a notion of size, which is the degree. And in integers, we have this notion of division, a divided by b. You get a quotient and a remainder, which is smaller size than the divisor. And similarly with polynomials, but size means degree. In the integers, you can use Euclid's algorithm to find the greatest common divisor of two numbers. And actually, same thing in polynomials. You can do Euclid's algorithm with polynomials, and it'll find the greatest, meaning highest degree, polynomial which divides evenly into both your polynomials. So you can try that for fun if you get bored. In the integers, we have a notion of what it means for an integer to be a prime. That means it has no non-trivial divisors, no non-trivial numbers that divide into it evenly. The exact same concept exists for polynomials, just has a different name. It's called irreducible. Okay, so there's a notion of what it means for a polynomial to be prime, irreducible. And the last thing I want to say, which is somewhat of the point of this slide, is one thing we saw 2 lectures ago is that if you take the integers mod p, you get a field if p is prime. Basically, the integers mod p have division. And it's the same thing true for polynomials. You can take the set of all polynomials over a field and mod out by a fixed polynomial p, which basically means you treat it as 0, like you always divide by it and take the remainder. It's a theorem that if this p is prime, then what you get, the object you get, is itself also a field. And the number of elements in that field is the cardinality of f to the degree of the polynomial. So I won't make you know this. This is sort of for culture's sake, but it actually answers the question, what are these fields of size 4 or size 8 or of size prime power which exist? I told you they exist. You can get them. You can get, let's say, the field of size 9 by taking all the polynomials with coefficients mod 3 and modding out by a degree 2 prime polynomial. Okay, so that's more advanced than I actually need to know, but I thought it would be fun to tell you that fact. Any questions about, let's say, polynomials and division with remainder? Yep. Right, so the question is, what does it mean, a non-trivial divisor? And it's sort of like, exactly with the integers, it's something whose size is bigger than 1, which in this case means degree bigger than 1. So it means a polynomial whose degree is bigger than 1. So any constant polynomial counts as a trivial divisor. Also an excellent question. Okay. Okay, so that's enough algebraic theory for now, such as you might get in an algebra class. I want to spend a little bit of time playing with polynomials. It'll still be kind of mathematical, and then we'll get to an application. Okay, so now this gets at a question that was asked early on about the role of the symbol x. So far, a polynomial to you guys is just a syntactic expression, and the x is just a symbol. But now we're going to talk about evaluating polynomials. Okay, so suppose you have a polynomial called p of x in some set of polynomials with coefficients from the field f. Okay, so if A is also an element of the field, I should have written that. If A is an element of the field, then P of A means its evaluation at A, which basically just means you plug in A for x. Okay, so if P of x is this polynomial, again with coefficients mod 11 and 6, which is an element of the field, you can look at P of 6. That means you plug in 6, you get whatever, 36 plus 18 plus 5, which is 59, but everything's happening mod 11. So it's 4. Okay, so P of 6 is 4, as you would expect. I'll do one more example. If you plug in 4, which is also a field element, you get 0. That can happen. And in mathematics, you enjoy it very much if you evaluate a polynomial and you get 0. It has a special name. You say that the number r is a root of the polynomial. Okay? Or sometimes you call it a 0 of the polynomial, but that's confusing. A root of the polynomial if it makes it evaluate to 0. Okay, so far not that complicated. But now let's look at the idea of the roots of polynomials, because it will shortly lead us to like the one and only theorem about polynomials. There's basically one theorem about polynomials, which is the great glorious theorem, which you always use and everything reduces to. It's very simple. It's about polynomial roots, and like the most sophisticated things like, this polynomial time primality, algorithm testing even, all reduce to this basic fact, which we'll lead up to in 2 slides. Okay, here's a very easy theorem. It's not the most impressive theorem. Let P of x be some polynomial which has degree 1. Then P has exactly 1 root. That's an easy theorem, which we'll now prove. Here's the proof. Well, P of x has degree 1, so that means it looks like some constant field element d plus some other field element c times x. And since its degree exactly 1, c is not 0. So, what could happen? If P of r, if r is going to be a root, P of r equals 0, just plug in it, it means c times r plus d is 0. So subtract d from both sides, divide by c, which is legal because c is not 0. And you just see that r is a root if and only if r is this one particular field element, minus d over c. Okay. That's the end of that proof. It seems trivial, but maybe if you're not used to fields, maybe it's not exactly clear 100% what's going on. Any questions? Okay, great. So the root situation for degree 1 polynomials is no problem. You just look at the coefficients, you figure out the root is whatever, minus d over c. Okay, so let's take it to the next level. Let's say P of x is a polynomial of degree 2. Then P of x, well, it's a question. You might have expected to hear that it has 2 roots, but let's investigate the situation. Here's an excellent polynomial, x squared plus 1. It has degree 2. One thing that's excellent about this polynomial is if you look at its coefficients, well, this polynomial has 3 coefficients. Can somebody tell me what they are? Yeah, 1, 0, which I didn't show, and 1. And 1 and 0 are in every field. So you can actually take this syntactic expression and think of it as a polynomial over different fields. So let's do that. So suppose I take this polynomial expression, and I think about it in this set of polynomials, where the coefficients are integers mod 2. How many roots does it have? I heard 1 vote for 0. I hear 1 vote for 1. It's 1. Okay? There's only 2 numbers in the field mod 2, so you can just check them both. There's 0 and 1. 0 squared plus 1 is 1. That's not 0, so it's not a root. But 1 squared plus 1 is 1 plus 1, which is 2, which is 0 mod 2. So if you plug in 1 mod 2, you get 0, so 1 is a root. Okay? All right. Let's go to the next one. What about if we think of this polynomial as having coefficients from F3? How many out of the 3 possibilities, how many field elements are roots? Well, 0 squared plus 1 is 1. That's not a root. 1 squared plus 1 is 2. That's not a root. 2 squared is 4, aka 1 mod 3. Plus 1 is 2. So that's also not a root. So actually there's 0. Okay, what about mod 5? Should I make you do it? Somebody said 2. Let's find out if that's correct. Yes, apparently it's 2. So you can check that 0 and 1 and 4 are not roots, but let's say 2 is a root because 2 squared is 4 plus 1 is 5, which is 0 mod 5. And 3 squared plus 1 is 10, which is also 0 mod 5. Okay, how many when we think of this as happening in the real numbers? 0. Yes, there are no real numbers whose square is negative 1. Okay, now get ready for complex numbers. How many roots does it have? Very good, 2 roots. I and negative I. Those are both, by definition, essentially square to negative 1. Okay, so a lot of different possibilities occurred. But what is the summary, do you think? Yes, somebody said between 0 and 3. I hope they meant inclusive on one side and... Oh, I see. Yes, between 0 and 2. So in fact, here it is, the single most important theorem you will ever need to know about polynomials. If you have a polynomial of degree d, it has at most d roots. That's the theorem. Okay. It's such an important theorem, we shall prove this theorem. So here it is. We'll prove it, as always, by induction on d. Okay, so the base case is that p is a degree 0 polynomial. Well, a degree 0 polynomial is just a constant, p of x equals a, and since it's non-zero, that constant is not 0. So no matter what you plug in for x, you just get a, which is non-zero. So indeed, this has 0 roots. Okay, so is the base case okay? There's some debate about the base case. Or something else over here? No? It's cool? All right. All right, let's do the induction step. So let's assume that the theorem is true for some fixed value d. And now we're going to prove it for d plus 1. So let p be some polynomial that has degree d plus 1. Okay, it's not too long of a proof, but let's go through it. So the first thing you say to yourself, hey, if p of x has 0 roots, then we're done. That's easy because, 0 is less than whatever d plus 1. Okay. Otherwise, it has at least 1 root. So let's say it has at least 1 root and call it b. Now, I'm going to remind you that we can have this sort of division with remainder in fields, polynomials over fields. So I'm going to divide p by the degree 1 polynomial x minus b. Okay, so when I do that, I get p of x is some other polynomial quotient q times x minus b plus a remainder polynomial. What can I say about this remainder polynomial? Yes? What's the simplest thing I can say about it based on the fact that I did this division algorithm? Okay, the simplest thing, is that, the theorem says that the degree of r is less than the degree of the thing that you divided by. You probably got that and are several steps ahead. But the degree of the thing you divided by is 1. So that means the degree of r is 0. Or maybe negative infinity, but either way, that means r of x is a constant polynomial. Okay? So r of x is some constant. Let's call it r. Next, we have this identity star. Let's plug x equals b into it. By assumption, b is a root, so the left-hand side is 0. Q of b is something. I don't know. This becomes b minus b, which is 0, so this all cancels out. So you get 0 equals 0 plus r. So you deduce that r must, in fact, be 0. So simplifying, we get p of x is q of x times x minus b. Okay, now p of x had degree d plus 1. And we've just written it as some polynomial q times a degree 1 polynomial. So if you think about it for 10 seconds, you'll see that that means q of x must have degree d. Because, this has like a something times x to the d plus 1 in it, so this needs something of the form x to the d to multiply against this x. Okay? Great. So now we can apply induction. Q has degree d. So that by induction, it has at most d roots. So now if you, again, look at P of x is Q of x times x minus b, how many roots can it have? Well, anything that makes p 0 has to either make Q of x 0 or x minus b 0. So it has to either be b, that's one root, or it has to be a root of q, of which there are at most d. So p has at most d plus 1 roots. Okay. Any questions about that? I went a little bit fast, but. Okay. Either you all got it, or you can look up the slides again when you're back home. Okay, so great. So we proved this most important of all theorems. And I just want to say, as a reminder, this is only true if the coefficients are a field. So for example, I don't really even want to allow you to do this, but if you tried to say, hey, let's have a polynomial where the coefficients are not over a field, like, or everything's happening over something else, like the integers mod 6, then you see it has degree 1, but it has 3 roots, 0, 2, and 3. I'll make this polynomial 0. Yeah, 3, because, wait a minute. Yeah, somebody just gave me like a look like, huh? And I think they're right. I claim that 3 times 3 is 0 mod 6, but that's wrong. This is good. You guys are paying attention. So 4? 3 times 4 is 12, which is 0. Okay, very good. All right. If I had a pen, I would write on my hand, like, correct these slides. Good. All right, we're safe. Thank you. Okay. One more theory-ish topic, and then we'll get to the application. But this is, I think, an enjoyable theory-ish topic, and it may come up for you in life. It's called interpolation. Let's say you're given a bunch of data points. What do I mean by that? Well, something like this. Okay? So these are pairs of points. So like on this axis, you have A1, and on this axis, you have B1. And you have a bunch of data points, A4, comma B4, A5, comma B5, etc. And suppose you're trying to explain this data. One thing you might try to do is fit a polynomial to it. So this is a question. Can you find, let's say, a low-degree polynomial which fits this data? It's a general question. So you want, OK, this picture is drawn as though all the numbers are living in the reals, but we're going to do it over a field. OK, so here's the problem stated a bit more carefully. Suppose somebody gives you a bunch of pairs, AI, BI, all from some field F. And I'm going to assume you have d plus 1 of them. It's a little unnatural to call it d plus 1 many, but let's say you have d plus 1 many. And a technical note, all the AIs should be distinct. You shouldn't have like 2 points on the same vertical line, because then you'll never fit a polynomial to them. OK, so here's a very nice theorem. There's exactly one polynomial of degree at most d which fits the data, which has p of ai equals bi for all I from 1 through d plus 1. OK, so if you want to fit 10 data points, you can do it with a unique polynomial of degree 9. Or if d is 1, it's saying like if you have 2 points, there's a unique line that you can draw through them. At least if you're imagining the picture in the reals. OK, clear on what the problem is, or the statement of the theorem is? OK, so we're going to prove this theorem now. So notice there are 2 things to prove here. Yeah, I mean, it doesn't look like it immediately when you say there's exactly one polynomial, but really that's telling you you have to prove 2 things. What are the 2 things you have to prove? Somebody put up their hand. Yeah. Yes, there's at least one polynomial, and also there's at most one polynomial. OK, so this is like existence, and this gives you the uniqueness. OK. Actually, number 2 is easier, so we're going to do number 2 first. OK? It's a little weird when you don't even have the confidence that some polynomial exists to try to show that there's at most one, but let's do it anyway. So I want to show there's at most one degree d polynomial, or degree at most d polynomial you can fit to the data. OK, so I wrote the theorem here. Let's say we have d plus 1 pairs from a field. All the AIs are distinct. I want to show there's at most one polynomial with degree at most d that fits the data, that has p of ai equals bi for each I. Here's the proof. It's quite short. Okay, so you say, sort of suppose, by way of contradiction, I guess, that p of x and q of x are two polynomials which both fit the data. Okay, and you can see on the last line, we're going to show that actually they're equal. Okay, and that indeed proves that there's at most one polynomial. If you show that whenever you have two polynomials that do it, they're actually the same. It's quite easy. So suppose p of x and q of x both fit the data. Just subtract them and call r of x the new polynomial. Now, p and q both have degree at most d. And if you add or subtract two degree d polynomials, you still get a polynomial of degree at most d. Actually, the degree can go down if you cancel out the high powers of x, but it can't go up. You can't introduce a higher power of x. So r is degree at most d. But now just evaluate r on each of the ai's. You get p of ai minus q of ai, and they're both equal to bi. So r evaluates to 0 on all of the ai's. Okay, and now we apply this theorem that I told you is the theorem you always need to know. R is a degree d polynomial. We know it has at most d roots, points that evaluate to 0, unless r is the all zeros polynomial. Okay, the theorem is if you have a non-zero polynomial of degree at most d, it has at most d roots. So therefore, r is the 0 polynomial. That means when you subtract p and q, everything cancels out, which means that p equals q. Okay? Question? Okay. All right, now let's prove the other part, that there's at least one polynomial. And this part is kind of fun, actually. It's sort of a bit like an algorithms problem. You're given this data, and you have to actually find or construct this polynomial that fits it. Okay, so this is what we want to prove. Given the pairs, there exists a polynomial that fits the data. Okay, so the algorithm or method for doing this is called Lagrange Interpolation. Because, of course, it was invented by a person that's not Lagrange. It was invented by an English person called Edward Waring. And then Lagrange invented it later. And he was the more famous mathematician. So somehow it got named after him. Okay, so let's do it. So here's the task. I'm going to write it in sort of a table like this. These are sort of the x-axis points, if you will. These are the desired y-axis points. We want some polynomial p that evaluates like this. Seems a bit hard. So I'm going to make it potentially easier. And I'm going to ask you to do it in a special case. Can you do this special case? The AIs, you don't know what they are, but B1 is 1, and all the rest of them are 0. That's what I want you to focus on. And the reason I want you to focus on that is because I'll tell you, once we solve this case, the general case will be quite easy. Okay, so I kind of assure you that this is possibly the hardest part. Okay. Can't quite remember what's on the next slide and whether I should click or not. Let's click and find out what happens. Okay. So this is the indicator that you should think about it. Possibly you've seen it before. Okay. Can some person, probably there's not enough time to actually figure it out if you're just thinking about it. So can some person, perhaps who's seen it before, give me a suggestion on how to do it? Yeah.
Let c of x be a polynomial, which is x minus a2 times x minus a3 times and so on.
Yeah.
And then,
Well, let's pause there. I think you probably know where to go with this, but let's pause here. So the idea was, let's try to get all the zeros right. Okay, there's something, forget the 1 for now. Let's try to get a polynomial which is 0 on all of these points. Well, that's not so hard. Construct this polynomial, x minus a2 times x minus a3 times dot, dot, dot. That has degree d, because you're multiplying d things. And it's pretty cool because its degree is d, and if you plug in any of these a2 through ad plus 1, the appropriate thing turns to 0, and you get 0. Only trouble is, you kind of have no clue what's going on with its value at a1. It's hard to say. I mean, you plug in a1, you get this, which is some number in the field. Okay, so this person who was going to answer the question before, what should you do? Yes, you should. See, you almost got it. You've got all the zeros right, and you've got some weirdo number here instead of 1. So just divide your polynomial by that number. And that will, all the zeros will stay 0, and that weirdo number will get divided by itself, and you'll get 1. You might think there's a few things to check here, so let's check them. So here's the more formal idea. Take the thing we started with that gets you zeros everywhere you want them, and then divide by this number in the bottom, which is the value of this the numerator at a1. So what could be a problem here? Yes? Yes, what if it's 0? You're not allowed to divide by 0. So what could be the solution here? Prove it can't be 0. Very good. That's right. So it cannot be 0. Why can it not be 0? This person? Very good. If you remember the hypotheses here, we're assuming all the i's are distinct. The only way this thing can be 0 is if you look at it for a second, if a1 is equal to one of the other a's. But it's not. They're all distinct. So the numerator is a degree d polynomial. The denominator is not 0, so it's OK to divide by it. And it's just a constant, so it doesn't change the degree dividing by it. And I claim it works. Okay, you get zeros for a2 through ad plus 1, and you get 1 for a1. Any question about that? OK, great. So we solved it in this very special case. Let's call this polynomial S1 the selector polynomial for a1. Great. What if these are the b's? Everything is 0 except a2 is 1. Can somebody tell me what to do? Yes? Yeah, it's the exact same thing. There's nothing special about the first guy here. Just do this exact same thing, but with a2 instead of the special thing instead of a1. So you get this, and I'll call that the selector polynomial for index 2. Okay? So if it's this data, all zeros, and then 1 at the end, it's the same thing, right? You can do the same trick, and you'll solve this interpolation problem, and you get some polynomial that works called s sub d plus 1. Great. So we've handled a small number of cases. Now let's go straight to the general case. So now what should you do? You?
Sum of all those earlier cases.
Yes. So you can build this using all the selector polynomials that we've built up before. So here's the solution. It looks a bit funny, but you take the S1 selector polynomial and multiply it by the desired height, B1, B2 times S2, and so forth, up to B d plus 1 times SD plus 1. So let's check why it's OK. First, it's supposed to be a polynomial of degree at most d. But that's OK, because all of these selector polynomials had degree at most d, and you're just adding them up multiplied by a constant. So the degree will not go up. Could go down. And it's supposed to have all the right values on the AIs. So why, for example, does it have the right value at A3? Did somebody say, yeah? And? Yeah. So if you imagine plugging in A3, sort of by construction, all the S's other than S3 are 0. So it doesn't matter that you multiply them by a BI, it's still 0. And then there's S3 sitting here as B3 times S3. S3 of A3 is 1 by construction, so you multiply it by B3 and you get the desired thing, B3. OK, so that is the end of the construction. Kind of like an algorithm, really. OK, so I don't know if I want to do this example. Instead, maybe I'll just let you look at it. So in this example, which you can look at on the slides, I'm going to carry out this algorithm. So over F11, that's the integers mod 11, I'm going to give you 3 data points. I want it to evaluate to 1 at 5, 2 at 6, and 9 at 7. So there's 3 points. So you should be able to fit it with a degree 2 polynomial. Okay, so first you get the selector for S5, which is some number times x minus 6, x minus 7. That knocks out, that will have values 0 at 6 and 7. and you fix it so that it'll have 1 when you plug in 5. And this guy, okay, so these are the selector polynomials. So this thing is 1 when you plug in 5, and it's 0 when you plug in 6 or 7. This is 1 when you plug in 6, 0 when you plug in 5 or 7. This is 1 when you plug in 7, and 0 if you plug in 5 or 6. And then to get the values 1, 2, and 9, you take 1 times S5 plus 2 times S6 plus 9 times S7. And it's a very long expression. But then in the end, you get some small degree 2 polynomial, which you can now check. Actually gives you 1 at 5, and 2 at 6, and 9 at 7. Okay. So most of the main work is actually figuring out what this coefficient is to get 1s in the selector polynomial. Any question? You should go home and practice this. Okay. Good. So this is a theorem, just a summary of what we proved. If you have pairs, d+1 pairs, data points ai and bi from a field F, the ai's are distinct. And if they're d+1 of them, you can always find a unique polynomial of degree at most d that fits them, has the target values. Okay. Last thing, representing polynomials. So suppose P is a degree d polynomial. There's 2 ways you can represent it by using d+1 field elements. What's the first way? If you need to tell somebody a polynomial using d+1 numbers? And yes? Oh, you also. Well, okay, fine. Ashu. Yeah, you just need to tell the coefficients. List the d+1 coefficients. But there's another way you can do it, which is interesting. Okay, yes? Yes, give the evaluation, or P's values, on d+1 different elements. Any elements of the field. And as we saw, that uniquely specifies the polynomial among degree d polynomials. Okay, so to go from representation 1 to representation 2, it's easy. If you have the coefficients and you want to get its values on, let's say, 1, 2, 3, 4 up to d+1, you just plug them in. And if you want to go backwards, if you have the value at d+1 different points and you want to figure out like what the polynomial is, like what the coefficients are, you do this interpolation algorithm. Okay? Does it make sense? Excellent question. I'm glad whoever asked that. Why would representation 2 ever be useful? I'm glad you asked that question. I will now give you an application to computer science in which representation 2 will be very useful. Okay. Application is to error correcting codes, which is a very important topic of study in theoretical computer science. And error correcting codes was invented by Shannon in like the 50s. And it's all about the problem of sending messages from one person to another person across a channel that is like a channel. I don't know why it's called a channel, but that's noisy. So you're transmitting a message, but like, you know, there's some noise in the world, so there might be some errors introduced into your transmission, but you still want to get your message across. Maybe you have some like very weak cell phone or Wi-Fi or something. Okay, so in computer science, there's always 2 people, and they're always called Alice and Bob, so here they are. Okay, so Alice wants to send a message to Bob. So maybe Alice is like, here's this cool URL I saw. Okay, so Alice wants to send it, but we're going to imagine that the channel causes trouble. Why are you guys on your cell phones? The channel is causing trouble, and it can corrupt some of the symbols. Okay, up to k symbols. It's also a problem because I'm going to start referring to Alice as her, but just deal with it. So how can Alice still get the message across? That's the fundamental question of error correcting codes. It's actually also if you're trying to store data on like potentially like a faulty hard disk, how can you store it in some sort of redundant way so that corruptions still allow you to recover the data? Okay, so let's say our messages are ASCII strings. So now I'm going to think of them as field elements. This is the cool application of fields. So we're going to think of messages as sequences of field elements from, I chose 257 because it's a prime. And it's a little bit bigger than 256. Okay, so maybe Alice wants to send this message, and ASCII it looks like this sequence of 6 field elements. Okay, so then she sends it on some noisy channel, and some of the field elements get screwed up. Okay, and Bob receives this, but wants to still know what Alice was sending. You might ask yourself, how can Bob correct these errors? Actually, there's an even trickier problem. How does Bob even know that there are errors? I mean, he might feel that the channel is buggy, but like, where are the errors? He just sees these numbers. He doesn't see the yellow highlights. Okay, let's start with an easier case where Bob doesn't have to worry about figuring out where the errors are. He just has to figure out recovering from the errors. This is called erasures. So erasures means Alice sends this string, and then the channel can just it's like a dropped packet, and like Bob knows the packet is dropped. Okay, so Bob sees like question marks in some of the symbols. It's like the bonus problem on the probability homework. Okay, so what can you do to handle up to k erasures? Suppose I promise you k is 2. You want to send a message, and the channel, we just know that it could erase up to 2 symbols, but you don't know which ones. What is a naive thing you could do to make sure you get your message across? Yes? How many times? If I promise you I'm only going to erase 2 symbols, how many times should you send each symbol? Yes, I hear a lot of votes for 3. So good. So this is a reasonable idea. It's called the repetition code. So Alice just repeats each symbol k plus 1 times. So if k is 2 in this example, instead of sending this, she sends this. It triples each symbol. And then, Alice and Bob know if only 2, in this case, things can get deleted or erased. Even in the worst case, they come from the same little block, but there's still 1 copy of the real symbol left over for Bob to figure out the message. Does that make sense? Okay. Now, it's a little bit worse if you don't have the erasure channel. That's Bob knows something got deleted. This trickier channel called the noisy channel, where just the symbol can change into something completely different. In this case, you can still get your message across using repetition, but it's a bit more expensive. You have to repeat each symbol 2k plus 1 times. So here's the message. Now I'm going to imagine k is 1, because there's only so much space on the slide. So Alice will still repeat each symbol 3 times. But now I'm saying the channel can alter one thing that is sent, but only 1. K is 1. So maybe it alters this one. Okay. So, but Bob can always still recover the original message. Why? Yeah, even in the worst case, each block you have 2k plus 1 copies. Even if the channel screws up k of them, if Bob just takes the majority symbol in each block, then he'll get the message. Okay? So far, so good, I guess. But this is not a very, as it turns out, efficient scheme. Okay, it's not the greatest idea. Because, look, say you're sending a message of d plus 1 symbols. Why d plus 1? Why not d? Well, yeah, you'll see. And you know that the symbol, let's go back to the erasure case where the channels that they're corrupted. The bytes are corrupted. Well, to guard against k erasures, you had to send k plus 1 copies of each symbol, so you had to do basically d times k symbols. Well, how good could you expect? Suppose Alice is even just trying to send 1 symbol, but the channel might erase k times. You gotta send Alice has to send at least k plus 1 symbols, right? Otherwise, the channel can just erase everything she sent. So if d is 0, you're going to have to do at least k plus 1 symbols. But you might hope that instead of d times k, you could get d plus k. That would be a lot better. So this is a great fantasy. Maybe for Alice to convey d plus 1 message symbols with k erasures, she could get away sending d plus k plus 1. Okay? And happily, this is true. So we're going to see how to do this using polynomials. Okay. Is the problem clear? And this is a good time to pause for questions about the problem. You guys know the difference between an erasure and a noise corruption? Okay, good. Okay. Polynomials. So here's an ingenious idea. Say Alice has a message of d+1 elements from some field. Let's say this one. Here it is. What Alice does is she thinks of these symbols as coefficients of a degree d polynomial called p. Okay, there's d+1 of them. And so she thinks in her mind that her message, she converts it to this polynomial. But instead of just sending this polynomial, which is sort of what she wants to convey to Bob, she sends it not in the coefficients representation, but in the values representation. Okay, so more precisely, she's wanted to send d plus k plus 1 symbols to Bob. So she just sends the value of this polynomial at the inputs 1, 2, 3, up to d plus k plus 1. So she sent sort of some information about her polynomial, in fact, redundant information, because she spent more than she would need in the values representation to recover p, although that's good because there's going to be some channel errors. This is called the Reed-Solomon encoding. It was invented by two ancient people called Reed and Solomon, Irving Reed and Gustav Solomon. Okay, so now if there are k erasures, Bob gets, yeah. Yes, as we'll see again at the end, it is actually used. Although this is a valid point, you do need some medium amount of computation power to actually compute these things. And there is effort going into algorithms for computing the message and also for Bob's task, which we're going to talk about, recovering the message from the values. This is an important aspect of research in error correcting codes. Okay, so in the erasure channel, Alice sent d plus k plus 1 values to Bob. K of them get erased, so at least Bob still knows p values on d plus 1 points. So why is Bob now happy? Yes? Do you have your hand up, or just? Oh. Yes, that's right. So the statement was, this theorem that we proved about Lagrange interpolation, Bob knows that Alice is sending a message of length d, so he knows that the polynomial she has in her head is of degree at most d, and he knows its value on d plus 1 different points. So now he can just do the Lagrange interpolation algorithm and figure out her polynomial, get the coefficients representation, and now he knows the message. Yeah?
How does he know that? What are those correct points?
Yeah, that's the question was, how does he know which are the wrong values? So this is one thing that makes analyzing the erasure channel, which what we're doing is nice. I'm promising you that in the erasure channel, Bob actually knows, like he actually sees 118, 114, and then he sees, oh, like there was a mistransmission. I know that I don't know what the value is here. So he knows all the positions that he doesn't have. Okay, it will get trickier when we go to the noisy channel where he just gets bogus values sometimes and he doesn't necessarily know. Okay, so I was going to do an example of this, like illustrating it, and I do it in like a math program. I like to use Maple. But then I was like, if I switch to Maple, then like the PowerPoint and the video, and it's going to be annoying. So then I just copied the Maple image. So I don't even know if it's worth doing this. Let me skip this, actually. So I was like, OK, let's do an example where d is 5, k is 3. You can't even read this. So, well, it works. Alice constructs some polynomial, and she sends the values on d plus k plus 1 points, the evaluations of the polynomial. Then I have the channel randomly select 3 things to erase. So Bob gets out, in this case, 6 values. But then the handy thing about Maple is we'll run this algorithm for you. So you can just say, hey, interpolate these 6 data points, mod 257. And it's like, here you go. Here's the answer. And then you tell it to simplify, and you get back this original message. So whatever. This is like a demonstration of nothing. It's like, you have to take my word for it. But, well, anyway, I mean, forget this example. We saw the proof. So it works. You can, I don't know, squint at this or try to do it at home yourself or on paper yourself. OK. All right. So, well, that's a cruel thing to say. Any questions about that? I mean, I can. All right. OK, so let's go to the harder case. This will be the last thing we do. What about corruptions, not erasures? Yeah, question? No question? Okay. What about corruptions, not erasures? So this gets at this question. It's trickier. Okay, so now I'm just going to tell you what Alice will do, and we'll see why it works. You know, before Alice just had a message of d plus 1 symbols, she thought of it as a polynomial. And to guard against k erasures, she sent the polynomial's value at d plus k plus 1 points. Erasures are trickier, so now she's going to send its value at d plus 2k plus 1 points. It's not so bad. It's still a lot better than d times k. It's like d plus 2k. So it's quite efficient. Okay, so let's try to talk through why this will work and Bob will still be able to recover the message. So we're assuming that the channel can corrupt, noisify, change k, let's say bytes, k symbols. So in some sense, Bob will now have d plus k plus 1 correct values of the polynomial. It'll look like this. He'll see p of 1, p of 2, then maybe he'll see some bogus value, then p of 4, some bogus value. Okay? But it's a problem because, again, he does not know where those yellow bogus values are. Okay? He does not know. He just sees like d plus 2 plus k plus d plus 2k plus 1 numbers. He knows that like most of them are right, but he doesn't know which ones. Okay? So it's a little tricky. Okay. Well, Bob is a smart guy. So here's the thought process. So Bob thinks to himself, okay, p of x is the message I'm trying to get, is a polynomial of degree at most d, and it mostly agrees with this list. Let's think about the extent to which it disagrees. So the true p of x disagrees with this list in at most k places, because the channel only gets to screw up k symbols. This is the best part. All right. So here's the key theorem. This is p of x, Alice's true message, is actually the only polynomial that has this property, that it only disagrees with the received message on at most k positions. Okay, how are we going to prove that? If we can prove that, then we're kind of good, because at least in principle, Bob can figure out what the polynomial is, if there's only one of them. Here's the theorem that we want to prove. The proof is going to fit here, so don't panic. Okay, here's the proof. Suppose, by way of contradiction, that q of x is some other polynomial that mostly fits the data, in the sense that it disagrees with the d plus 2k plus 1 transmitted symbols, except in k positions. Then, p of x and q of x disagree with each other in at most 2k positions. Because p of x has some set of values, q of x has some set of values. There's some third set of values, the ones that get sent to Bob, which p and q both mostly agree with. They only disagree with this third thing in at most k spots, so they can only disagree with each other in at most 2k spots. Does that make sense? Did you get that? Okay, and still this q of x is like a hypothetical polynomial. Good. So just subtract. We know p of x and q of x disagree on at most 2k values. There's d plus 2k plus 1 total values. That's how many Alice sent. So subtracting, p of x and q of x agree with each other a lot. They agree on at least d plus 1 positions. Okay, so now why are we done? Yeah? Right, by the theorem we showed, if you have two polynomials of degree at most d, and they agree on d plus 1 positions, then they must be the same, because we know, if you have d plus 1 data points and you try to interpolate by a degree d polynomial, there's a unique polynomial that does it. Or if you want to remember the proof, you can say, consider p minus q, that has degree at most d, and it's going to be 0 on all these positions, of which they're d plus 1. Degree d polynomials have at most d roots unless they're the 0 polynomial. So that proves that p of x equals q of x, which means that there's a unique polynomial p which has such good agreement with the data. Any question about that? So now we're kind of home free, except for one question that was alluded to earlier. So Bob, he gets this data. He knows there's a unique degree D polynomial which disagrees with the data on at most k positions. It's unique, so he can, in principle, recover P. So can somebody say one way he could do this? Somebody who is not banned. Come on. All right. Yeah, sure, yeah. Yes, test every possibility. Well, what exactly does that mean? Maybe, yeah.
Well, if you test at least a lot of the possibilities, the only ones that should be the same are where you have the correct polynomial. If you have only corruptions, they should generally differ from each other.
Yes. Can somebody give me like a much more explicit, yeah? Yes, more or less, yeah. So this is like the brute force algorithm, which is suggested by both people here. Try all possible d plus 1 sets of values, interpolate by Lagrange interpolation to get some polynomial of degree at most d, and then check if indeed it is agreeing in at least d plus k plus 1 values. And we know that there's only one polynomial in the whole world. There's exactly one which agrees on this many values. And in the case that Bob actually selects the d plus 1s which are correct, he'll find that polynomial. So eventually you can do it. It's not super satisfying because that's a very slow algorithm. And one would like to improve it. So the brute force algorithm here actually takes time that's like exponential in d, which is not satisfying. So a guy called Peterson in 1960 gave a polynomial time decoding algorithm for this problem. It's like a non-trivial problem. You've got a list of data points, d plus 2k plus 1. You kind of know that there's a degree d polynomial that mostly matches them. It's like interpolation with some errors. You have to find this polynomial which mostly matches them. That's tricky, but he did it with a polynomial time decoding algorithm. It was actually even before the notion of polynomial time was invented, so it's pretty cool. Then these people are famous because Berlekamp and Massey because they gave like very practical versions of this algorithm, okay? And they actually made this whole Reed-Solomon encoding transmission process, the decoding especially, practical. And actually, CMU's Professor Guruswamy, who sometimes teaches 251, also has worked a lot on this question. He in fact has efficient algorithms that can actually correct more than a k fraction, k corrupted symbols, although you have to exactly say what that means. But he's done some very famous work on this topic. And the last thing that somebody asked, this seems maybe impractical, but in fact they're used in practice. So all of these things are all Reed-Solomon codes. I mean, they're arranged in like a two-dimensional grid for reading purposes, but they're all Reed-Solomon codes. So these things are really used in practice. Okay, that's it. Quizzes.